All right. Assalamualaikum. Welcome back, guys. So now let's continue our previous discussion that we are still we done for the studies question. Now we are moving on to the real practice exam. So as you can see, this practice exam we prepare to get used to answer question, particularly about internal energy, heat, calorimeter, and then others. Okay, so let's let's get started to solve all of the problems. All right, the question is, if a system internal energy increased to 150 kilojoule after the addition 375 kilojoule of energy as heat, what was the value of the work in the process? Remember, the key concept of this type of question, okay, if system internal energy increased to 150, energy internal, which mean delta E, 250 kilojoule, increase, right, after the addition, and then the heat itself, okay, 375 kilojoule. So this one is the concept of first law of thermodynamic, which says delta E Q plus W. Okay. So delta E over here is positive, right? Because increasing. Okay, delta E is increasing. So positive. And then Q is addition, which means it should be positive as well. Okay, so 375. How about the value of the work in the process? Work in the process. So what's the meaning of work in the process? Let's see. So W is, okay, W is let me think. 250 minus 375. Okay, so the answer would be minus 125 kilojoule. So the answer will be B. So sometimes the thing that make us making a mistake here, okay, made a mistake over here is we plug the wrong sign, okay, minus becoming plus, plus becoming minus, kind of like that. Okay, so the answer is minus B. Okay, the negative signs over here telling us what the system did work on the surrounding, okay, work on the surroundings, okay, surroundings, or we can say it lost energy, as work. Okay, it lost energy as work. Okay, just quick tip, just arrange like if the answer negative, the system did work on the surrounding. If W is positive, that will be the work done on the process, on the system, sorry, on the system, not in surrounding, right? Okay. Now number 2, if 345 kilojoule of energy is transferred to system as heat while the system does 42 kilojoule of work, what will be the change in the internal energy of the system after the processes are complete? How to solve this problem? The key concept again, delta E Q plus W. Okay, before we are going through solving this problem, we need to understand like which the formula we need to use. Okay, which formula we need to use. It depends on the type of question. as you can see, guys, if the energy, this is the energy, okay? So we can say what's the meaning of energy over here is or the energy here is transferred to a system as heat. As heat. This is the clue. Which mean is telling us, guys, which mean is telling us that is kind of like telling us, okay, this is Q. Okay, this is Q. So remember this option. I mean, remember kind of like this type of question. Whenever you are facing the question about like heat, work, and then what else? Internal energy. So it will, I mean, it will involve, right? Uh, kind of like the first law of thermodynamics. Okay, so as you can see, guys, 345 key is 345 kilojoule. While the system does work, okay, so W, if system work, I mean the system does work, so which mean it will be positive 42 kilojoule. What will be the change internal energy of the system after the process are complete? So remember. So remember in this case, let me, wait, what will be changed in the, okay, while the system does 42 kilojoule. Let me think, it should be positive, right? If this one positive, looks like the answer will be either B or I don't know. Let me think. Oh, sorry, guys. Sorry. Let me clarify again. Okay. So again, as heat, while the system does 42 kilojoule of work, what will be change in the internal energy of the system after the process is complete? So this time Q is positive, right? Energy is transferred to system. Okay, transfer to system. So for example, we have system, we have surrounding over here. Okay, we have system, and then we have environment outside. And then to illustrate this problem, okay, so energy from surround, okay, from surround or from around the system, kind of like transfer to the system. Okay, transfer to the system. So Q will be positive, which mean the heat increasing. Okay, heat increasing. Okay, like we are mentioning in the previous part, guys. So did you remember it? So in this part, so you see heat release Q negative. Okay, heat release Q negative. So in this case, Q is not released. The system capture heat. The system capture heat, not releasing, but gaining heat. So it will be positive. And then which one that word? Which part that word? So environment or system? It should be the environment. So if the system, I mean, if the system and if the was that the work done in the system, so that will be the answer. The key, the W will be negative. Sorry, 42 kilojoule. Okay. So the negative sign over here, guys, remember, the system did work on the surrounding. It lost energy as work. It lost energy as work. So, like, the system did work on the surrounding here, not on the system. Okay, remember, the system did work on the surrounding. Okay, again, the system work on the surrounding. Okay, so the answer will be what? 345 minus 42. So the answer will be 303 kilojoule. So the answer will be B. Okay, the answer will be C. Sorry, the answer will be C. Okay, so the system internal energy is increases, right? But not by the full amount of heat added, because some is lost as work done by the system. Okay, always remember, Q positive if Q will be positive if heat is added, and then W will be negative if the system does work on surroundings. Okay, just remember this one. And then be careful with the sign. Okay, be careful with the sign. The system internal energy increase, but not by the full amount of heat added, because some is lost as work done by system. Because system does work. So the key is over here. The key is over here. Does work. So kind of like it lose some energy from the system. So let me give you the illustration. So now now we try to know the real world explanation. Okay, the real life illustration example. Okay, so okay, now let's talking about Q. Okay, let's talking about Q, how to make it more memorable. Okay, so for Q, just illustrate kind of like this. If someone's give you money, okay, if someone give you money, your bank account will increase. Okay, so if someone give you money, okay, your account will be increasing. So in the thermodynamic, if heat is added to the system, so remember, system is your bank account. Okay, bank account. Okay, and then like the money deposit or withdraw, deposit and withdraw is energy transfer. Okay, So if someone gives you money, okay, or you receive deposit, your account increasing. So if in the thermodynamic, if heat is added, it is added, it will be what? Q will be increasing. Q will be positive. If you pay something or money leaves your account, okay, your account will be decreasing, right? If heat is lost, it is lost. So Q will be minus. Q will be negative. Okay. Now let's move on to work. Okay, this is this for Q. I think there is no issue, right? So it depends on our understanding. So just illustrate the system is kind of like paying account, paying your paying system, and then as you can see, if we are like apply with this system, if this equation, so 345 energy is transferred to system, which means you deposit something, so your money will be increasing. It means in the thermodynamic, your Q will be what? Will be increasing. Okay. And then now let's move on to W, which means the work. Okay. Work. If someone deposit money, if someone deposit money as a gift, okay, if someone deposit money as a gift because work is done on you, your account will be increasing. Okay, just remember this one. Okay, like I mentioned, if someone deposit money as a gift for you, okay, so in the thermodynamic, if work done, okay, is done on the system, so W will be positive. If you pay bill, okay, you do work on someone else, okay, your account will be decreasing. In thermodynamic, if work done is done by the system, so W will be negative. Okay, so uh in real life scenario, kind of this one, you receive $100 as birthday gift, for example. So you receive $100 as birthday gift, like Q plus $100. Okay, you pay for groceries, like $30. So you pay something else. Uh, you pay groceries. Work done by you. Okay, work done by me, for example, minus 30. Okay, remember, if someone transfer me $100 and then I buy something, okay, you pay $30 for grocery, which mean W will be decreasing, okay, or minus. How much does your account change? So it's simple. W is key minus W, so it will be 770. Okay, just remember, heat edit energy comes in. Okay, heat edit energy comes in. Heat release energy leaves. Okay, like paying for meal, paying for your grocery, like gift deposit, and for heat edit, uh like a gift deposit. Okay, and then if work done on system, remember work done on system. Okay, someone else deposit money. Okay, someone else deposit money. Okay, so work done on system. Remember, work done on system. Someone else deposit money. And then work done by system, you pay someone. Okay, you pay someone. Just remember, kind of like into the system positive, out of the system negative. Okay, all right. I'm still done. I mean, I'm still for heat is okay, but for W. Mm, so energy left by the system. The system does work. Okay, the system works, so 42. Okay. Okay. So I got the thing that so easy to memorize. Okay. So imagine you have the balloon. Okay. Balloon is kind of like the system. Okay, let me draw it over here to make it easier. If you have kind of like balloon, okay, you have like kind of like balloon. Balloon itself is system. Okay, balloon itself is his system. If the system is pushing out when you blow it up, okay, when you blow up a balloon, okay, the balloon will be bigger, right? Will be bigger, will be pushing out, expanding, doing work. That balloon, that system. So let me, okay, imagine you blow up the balloon, then let it go without without tying it. Okay, you don't tying it. Okay, without tying it, and then the balloon flies around the room, pushing air outside in as it shrinks. Okay, pause it first. Okay, let's continue our discussion. So, because of this one is kind of like much more complicated, guys. So, kind of like I need to understand as well, to be better under to get more understanding, like how to describe the equation. Um, like I mentioned, uh, like if you have a balloon and then you blow up balloon, right, and then you let it go without tying it, okay, the balloon flies around the room, okay, pushing air out as it shrinks, okay, pushing air out, okay, as it shrinks. All right, the system in the air inside the balloon, when the balloon expand and push on the air outside, it's doing work on the surrounding. It's doing work on the surrounding, which mean W will be negative. So work done by the system. And then imagine now you have a balloon and then you squeeze it. Okay, squeeze it with your hand and make it smaller. The outside force your hand is compressing the air inside. Okay, in the thermodynamic, the system is still the air inside the balloon. Okay, when you compress it, work is being done on the system. So work done on the system, which means W is positive. Okay, just quick table, like quick information to remember. Okay, system does work. Okay, energy will leave system and then it will be negative. Okay, so you have a balloon, you blew up, and then you let it go without tying it. Okay, and then the air you push you and then this balloon will push air out, okay, as it's shrink. Okay, so it means like the energy will come out from the system to surround, okay, to surround. And then so this one is system does work. Okay, system does work. So system work and then give something to surrounding. Give it something to surrounding. So it will be W will be negative. However, when you have the balloon and then we squeeze it, all right, squeeze it more. So work done on system and then energy enter the system. So balloon squeeze and becoming smaller one. Okay, so if you squeeze in compressing, so work is done by system, which means you give it energy in the system and then energy will be positive. Okay, I gotcha. I got the concept right now. Okay, all right, so now let's move on to another part. Two metal sample of the same mass and initially at 25 degrees Celsius are heated so that each metal receives the same amount of the thermal energy. Which metal will have the highest final temperature? So now it's correct. It's this question is telling about the specific heat. Okay, specific heat itself, like the previous one, as I mentioned, like specific heat. Again, specific heat, if you have, okay, it tell us like how much energy is needed to raise the temperature of 1 gram a substance by 1 degree Celsius or 1 degree Kelvin. So lower lower specific heat will, okay, heats up more because of what, like I mentioned, specific heat is kind of like how much energy needed, okay, how much energy is needed to raise the temperature of 1 gram by 1 degree Celsius or 1 Kelvin. Okay, so if you see the energy specific heat capacity is lower, it means like we only need like a little bit a bit energy to heat it up. So if we apply the same if we apply the same energy, however the we have a lower the capacity energy, it will heat it up more rather than the higher one, the higher specific heat capacity. Okay, so as you can see guys from here, QMC delta T. Okay, delta T. This is by this concept. Okay, we can understand by this concept which metal have the highest final temperature. So the specific heat of X is this one. This one is specific for others, for Z. So like I mentioned, if the specific heat is lower, okay, it will increase the temperature easier. If we are applying the same energy, such as this one, each metal receive the same amount of thermal energy. Okay, which one did the highest? The highest will be X. Why? Because of it has lower energy heat capacity, so it will achieve like the not the threshold, kind of like when it will be heated up at that time. Okay, so like it will increase more because it has lower capacity. Okay, if you see these figures, is the equation delta T is what? Q divided by M per C. Okay, so mass is same, right? And then C, no, the Q is same. Wait, the Q. Okay, if C lower, okay, yeah, mass same. Okay, mass is same. Okay, the information is just mass. If the C is lower, okay, you will get much more delta T. Okay, lower, this one it will be higher. So which one that lower? This one. So X will be higher one. Okay, the correct answer will be A. Based on this information, when a cold block, let's move on to another part, another question. When a cold block of aluminum at 0 is placed in room temperature water at 21 degrees Celsius in insulated cup, the water, the aluminum end up, the final temperature is minus 19. Assuming there is no heat loss to the surrounding, which statement best describe exchanging this process? Okay, as you can see guys, there is a cold block aluminum, and then at 0 degrees Celsius is placed in room temperature water, and then water is 21 degrees Celsius. And then when we are mixing together, I mean when we are combining together, so the final temperature is 90 degrees Celsius. So what's the conclusion from this one? We can use what? Okay, we can use in insulate and system energy is conserved, right? So energy loss by the water will equal energy gain. So no energy loss to outside, right? Because here no heat loss. Okay, and then aluminum start cools and warmer. Okay, it gains energy. So aluminum will be gain energy. However, water will lose energy. Okay, so which one that gain energy? The block of aluminum gain the energy. Yes. Then the water loss, because as you can see guys, aluminum will absorb the heat from the water, and then it will increasing the temperature, which mean the aluminum gain the energy. And then water, originally the temperature is 21. However, when both are combined, okay, it decreased to 19 degrees Celsius, which tell us that water is like the water loss energy, not gain energy. So the answer will be B. Okay, number 4 is B. Okay, now just quick recap for this issue, for this problem. Okay, just quick recap from the number 3. Just remember, lower specific heat greater temperature rise for the same energy. Remember, lower specific heat capacity will produce higher temperature with the same energy, for the same energy. Okay, and then for number 4, in insulate calorimeter, there is no energy lost into the surrounding. Okay, so insulate system, right? Insulate system. So there is no energy loss. There is no, I mean, there is no energy going outside. Okay, going outside. No energy lost to the outside. Okay, because of in the, like here, no heat loss to the surrounding. So heat loss will be same with the heat gain. Okay, with gain. Okay, just remember that one. And then number 5, a piece of iron is heated 95 degrees Celsius. A piece of iron heated to 195 degrees Celsius. Then the temperature of system, then place an insulated vessel containing 250 gram of water, and then now is water, and then this one is 25 degrees Celsius. When the system comes to equilibrium, the temperature of the system is, when it combine it together, right? So it's 35 degrees Celsius. What is the mass gram in the iron? Assume no heat is lost to the surrounding. So kind of like the previous one. However, we need now we need to do calculation. We need to do calculation. So which one that gain energy? Which one that gain energy? It will be water, right? Which one will be gain energy? So gain energy will be happen in the cold object. So the colder one is water. Okay, so how to know this one is very easy. Just Q MC delta T. So over here, Q MC delta T, Q MC delta T. So like I'm mentioning before, that energy lost by the water same with the energy gained by water. Like the previous one, energy lost by water, same energy gained by the aluminum. So now still same, guys, still using the same kind of like, what is the one? Oh, I think I make a mistake. Number 5. Okay, now let's take a look at the answer of this one. I just want to make sure my understanding is correct. Okay, key concept. Okay, this one is calorimeter problem again. So like I mentioned, Q, okay, loss plus Q gain will be 0. Okay, Q loss, Q gain will be 0. So Q loss will be minus Q gain. Which one that gain? Water, right? Which one that gain? Water. So minus MC delta T of water. And then which one that Q loss? Iron, right? So MC delta T of iron. So now the question is about mass. Okay, the question is about mass. So what is the mass of iron? Okay, C of iron is 0.450, and then the delta TE will be what? The delta TE will be, the initial part is 95, and then so 35 minus 95, so it will be minus 60, and then this one is 250 gram, right? 250 gram, remember? However, it should, yeah, this one is correct. We don't need to convert it into others. And then C is 4.814, and then delta T is this one. This is the final temperature. This is the initial temperature. So 35, and then should be 10. Okay, so from here we can get we just do calculation stuff. So M will be 0.450 times minus 60. So it will be minus 27, and then 250 times 10 times 4.8. It will be 10,460. Okay, this one is minus. So M, it will be what? Divided by 27. It will be 387.40. So it will be C for the answer. Yes, it will be C, the answer. Okay, just remember this equation when we are dealing with the information, kind of like this one. Calorimetric problem. Okay, calorimetric problem. Okay, now number 6. When 45 gram sample of an alloy at 100 degrees Celsius is dropped into 100 degree gram of water, 25 degree, the final temperature is, this one is still same concept. Use the Q gain, same with the Q loss. Okay, so alloy, the initial temperature is 100, and then water, the initial temperature is 25. So the final temperature is 37 degrees Celsius. Which one that gain energy is water? Okay, so MC delta T, okay, of water, and then again MC delta T of alloy. And then we already know this is water, 100 gram, and then the temperature from 37 minus 25, it will be 12. And then C is what? C water is 4.8184. Okay, and then M here is 45, and then the equation is C, and then again 37 minus 100. So this one is minus 63. So what's the heat capacity over here? 100 times 4.184 times 12 divided by 45 times 45 times 63. So the answer will be 1.771. Okay, number 6 is B. Okay, this is calorimetric. Okay, again, when 68 joule of energy are added to sample of gallium that initially 25, the temperature rise to 38. What's the volume? Now the question is about the volume. There doesn't matter. Okay, so like the previous one. Gallium initially has temperature 25 degrees Celsius, and then the temperature rise to 38. What is the volume? Okay, what is the volume? So now we have like another type question, not kind of like the previous one, which is about the calorimetric. This one is, yeah, still calorimetry. However, we don't use kind of like Q gain and then Q loss. No, we just use the Q MC delta T. Okay, the Q, okay, the Q we already know is 68 joule, and then the C is 0.372. And then how about the delta T is this one, 38 minus 20, 30, 38 minus 25. So it will be 13. How about the mass over here? So when we got the mass, we will get the volume. Okay, 68 divided by 0.372 divided by 13. So it will be mass is 14.061 gram. And then how to get the volume is simple. Rho m per v. So what's the rho is, how to get the v is m per rho. So 14 0.61 and then 5.904. So divided by 5.904. So it will be give us 2.33 centimeter cubic. Oops. So the answer will be A. Number 7, the answer will be A. All right. So now move on to relationship between temperature change. Okay. So a student mix 100 milliliter of what 0.50 molar NaOH with 100 milliliter of what 0.50 HCl in styrofoam cup and observe the temperature increase of delta T. So delta T1 increase. When she repeat the experiment using 200 milliliter of its solution, now change 200 milliliter, she observed a temperature change of delta T2. If no heat loss to surrounding or absorbed by the styrofoam cup, what is the relationship between delta T1 and delta T2? Okay, how to get this one done? Just still same concept using QMC delta T. Okay, now when you double both volume, the amount heat produced also doubles. Okay, because there are twice as many reacting moles. Okay, because there are twice as many reacting mole, but the total mass of solution is also double. So like this one. So in the first part, you have QMC delta T, right? QMC delta T, and then another one, this is delta T1, and another one is QMC delta T2. So when you double volume, you will double for the mass. Okay, when you double when you double the volume, you will double like this one, right? When you double the volume, for example, the volume is 1, like just 2, for example, 4 divided by 2. If you double this one, so you will double the mass. Okay, for example, based on this equation, okay, like, okay, let me show you. Volume is mass per row. If you have V1 and then V2, like for example, this one is, for example, 2, and then your mass is 4, and then your row is 2, and you want to double, so it will be 4 and then still 2, right? Density is still same. And then how about this one? The mass will be double as well, right? So it will be A. Okay, so the mass, it will be double as well. So as you can see, in this part, your mass will be just 1. Okay, and then this one, it will be the Q will be 2. So what's the correlation between this and this? Like I mentioned, it's very easy. It will be doubling delta T. Okay, so the correct answer will be this one. So if we have, okay, we can cancel out this one, cancel out this one, cancel out this one, cancel out this one. No, not cancel out Q. Okay, so we have what Q, like M delta T1, Q, and then double to M delta T 2. So the question is only about delta T. Okay? So how to get delta T is pretty easy. Just Q divided by M. Q divided by M. Okay? And then delta T2 as well, Q2 divided by M2. So like this is M1. Like I mentioned, if you're doubling this part to M, what's happening for delta T? Okay, what's happening with delta T? So it's kind of like you just put it over here. I just want to put it over here, okay, based on this correlation. So Q1 or M1 and then Q2, right? And then M2. Oh, no way. Why I'm confused? So Q2, okay, will be doubling to Q1, right? Because like I mentioned, because it should be 2. Okay, the mesh should be 2. Just assume the first one is 1 and then the other one is 2, like the based on this illustration. And then you will have ended up getting Q2 over here. Okay, Q2 over here. So, and then because M1 is 2M2, right? Okay, so how to get this one done is pretty easy. Just to Q1 is 2M1 and then C and then delta T2. It's same with the Q1 M1 C delta T2. So delta T2 will be delta no way. So like I don't know what's the correlation. Number 8. Yeah. Will be delta T1. Correlation is should be same. That's interesting. Oh, the difference is only Q. The difference only Q. T1 in T2 still same. I'm so sorry. Okay? Just remember. Okay? Heat release, so QMC delta T. If both heat and mass double, we can put it in kind of like this one. Q will be double, right? Q will be double because we have 2 over here. And then M will be double. Okay? And then, as I mentioned, but QMC delta T. So, 2Q1 will be 2M1 C delta T2. Just the difference, just M1. And then, same thing with the Q1. Q1 just M1 as say C1 delta T1. So, the correlation between both is kind of like this. Still same. There is no issue. Okay, just quick recap. Doubling both amount of heat and total mass solution doesn't change the temperature increase. The ratio still same. Okay, the ratio still same. All right. Now move on to another question. So remember, there is so if the question is kind of like you are asked about what's the correlation between Q1 and the Q2, yes, you will get the answer kind of like Q1, okay, will be Q2 will be 2Q1 and then M2 will be 2M1, kind of like that. But for temperature, nothing. Okay, temperature, nothing. Not having any kind of like change. Okay, so now move on to another part. Okay, now iron can be converted to Fe2O3 according to the reaction below. How much heat in kilojoule is required to convert 10.5 gram of iron to Fe2O3? Okay, now we use kind of like moles equation and other stuff from balance equation. So 2Fe plus 3CO coming Fe2O3 plus 3CO2. Iron can be converted to, okay, blah, 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 blah. And then how much heat is required? Convert 10.5 gram of 10.5 gram of what? To convert iron into, oh, the iron itself is 10.5 gram. Okay, now we need to know the moles of Fe itself. Okay, the mole itself is just divided by 55.8 gram per mole. So we will get the mole of Fe over here. So the answer will 0.188 mole. Okay, so 0.188 mole. So now the question is how much heat in kilojoule is required. Okay, this is the mole itself. Okay, so from the balance equation, Fa, okay, from the balance equation, Fa is this one, to 6.8. To mole Fa to 6.8. If we just want to convert one Fa, not two Fa, it means we just divide it by 2. So the answer, oh, no way. No, not like that, I think. Not like that. We need to what? We need to use the mole equation. Okay, so Q, okay, Q, and then 0.188 divided by 2, okay, because half mole, okay, half of this mole, and then times what? Times this one, 26.8 kilojoule. So it will be 2.52 kilojoule. So the answer will be B. Okay, so remember, if we just want to know one, so we need to divide it this one first and then times this one. Okay, times this one. So Q kind of like mole times delta H, the equation, mole times delta H. All right, now we are moving on another part again. So what is delta H for reaction if 0. Blah 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 release blah blah blah. Okay, 0.152 mole sample, this one react completely according to the reaction shown. Okay, what is the delta H of reaction? What is delta H of reaction? Okay, now we take a look at the balance equation again. CH2O2 plus O2 becoming to CO2 plus 2H2O. Okay, now we need to take a look at one by one. CH2O2 is 0.152 mole. And then it, like, this one was released. Heat is released. So what is delta H for this reaction? Okay, so now the key concept still the same. Delta H is per 2 mole CH2O2. Okay, so we need to divide this one by 2 again. 0.52 divided by 2. So it will be 0.076. And then we need to was that. So we need to times, let me think first. So for for 0.152, heat release is 38.7 kilojoule. What is delta H for this reaction? So it will be 2 divided by 0.152 times 38.7. So it will be what? It will be 509 kilojoule. Because its heat release is would be negative. Okay. Hmm. So let me do. Oh, I got you. Man, why I forget. Okay, so as you can see, guys, we can use this coefficient to be mole. Okay, so now remember 0.552 mole will release 38.7 kilojoule. Okay, and then what if we have 2 mole? What's the kilojoule over here? Okay, it's pretty simple, but why? 38.7 times 2. X will be 509. Yeah, minus. Okay. Okay, again. This one can represent the mole. Okay? Can represent a mole of CH2O2. So, 2 mole. However, based on the equation, if we have kind of like such as this mole, it release this one. And in the balance equation, we have 2 moles, and then how much energy release? Okay, that's great. That's great. Okay, again, 1 gram sample, this one is decomposed in a bomb calorimeter. In a bomb calorimeter, the temperature increased by 6.12. What is the molar heat of decomposition of NH4NO3? So remember, a bomb calorimeter problems. Okay, Q C delta T, and then this one. Okay, HF, and then M equal Q. Okay, still Q C delta T, and then delta HF Okay, delta H is kind of like this one should be M, right? And then this one Q. Is this right? Yes. Okay. So now we need to know what the temperature increase 6.12. So the question is the composition. The molar heat is molar heat of the composition. Okay, let's see. Let's take a look at this one. 1 gram sample. Okay, we can put it over here, guys. Gram 1 per 80. And then what else? The temperature. Okay. Okay, we can put in such as this way. C delta T. Okay. And then calorimeter constant is 1.23. Then delta T is 6.12, right? This is M. So what is the molar heat? Okay, let's take a look at this one first. Yeah, the question is about delta H, right? I just want to make sure this one is correct. 1 divided by 80. So delta H 0.0125. And then 1.23 times 6.12. 7.52 divided by 0.01. So delta H will be 602 because molar heat is okay. Because the temperature increase, so the reaction is exothermic. So delta H will be negative. The temperature increase, so it will be exothermic, and then delta H will be negative. Okay. So why delta H is negative is because the temperature increase. Okay, the temperature increase. So remember, for example, we have the system, right? The system, and then we have the surrounding. So over here, our perspective is in surrounding. Okay, in the surrounding pump calorimeter, the temperature is increased. Okay, delta H the temperature is increase. So delta H will be minus. Okay, so now just remember, if temperature increase in the surrounding, okay, in the surrounding, so it receive heat from the system. So system will release the energy. So we can describe it as exothermic. Okay, exothermic, exit the energy release, so the heat is exit, right? And then the surrounding becoming heater, like becoming more heat. Okay, because the temperature rises because that heat nowhere else to go, like the surrounding feel the heat. However, if the temperature decrease, if remember your perspective in the surrounding, okay, if the temperature decrease, so it will endothermic, so the system will absorb the heat itself. Okay, the temperature of the surrounding calorimeter decrease because it's being taken by the reaction. Okay, that's great, that's great. This is the concept of pump calorimeter. Okay, just remember the equation is delta H m c delta T. Okay, remember this one. Okay, remember this one. Okay, delta H m c delta T. Okay, now we are going to number 12. 1 gram sample glucose is burned from calorimeter. The temperature of calorimeter is rises by 9.40, rises by 9.40. What is the heat capacity? Same thing, delta H, and then we have M, we have mass, right? And then C, and then delta T. Okay, so the question is heat capacity, C. Okay, the question is C. So just plug over here, uh, the delta H combustion is minus 23 times 10.3, and then M is 1 gram divided by 180.2, and then C, and then delta T is 9.440. Just doing like basic calculation, 2.83 minus, right, divided by 180.2, and then divided by 9.440. It should be minus 1.67. Okay, it should be B. The answer should be B for number 12. For number 11, A, that's correct. And then for number 12, it's C. What's going on? What's going on? The decomposition minus delta H combustion. Hmm. Yeah, it should be B, guys. It should be B. Hmm. I think there is something issue with the key. The key is C. So heat release, right? Bomb calorimeter. The reaction release heat. Why release heat? Oh, the calorimeter is absorb energy, right? And absorb heat. So we use the positive sign over here. Since the reaction release heat, the calorimeter absorb it. Okay, so we do kind of like see 15.71 divided by 9.40. 15.71. So it use positive, not negative. So just mole first, right? And then we get like 0.0055, and then release, heat release. So Q moles delta H, right? So 0.0055 times combustion is minus 2.83 blah 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 10 to the minus 15 kilojoule. So now because the reaction release heat, so the Q will be positive. Q will be positive. I don't understand. Oh, oh, this- okay, okay, okay. Okay, let me break first, okay? Let me break and then we want to continue later on. I'm like getting confused why I kind of like make so much mistake today. All right, it's okay. It's pretty normal. Okay.